The next couple fields I want to talk about are perhaps the most important, really the whole reason the IP protocol exists, and those are source IP address and destination IP address. And you'll see those are found in the 1, 2, 3, 4th, and 5th rows here, and IP12 and IP16 bytes offset from 0. And of course, the source address is the host that sent the packet, and the destination IP address is the host that should receive the packet. I say should because IP is not really a reliable protocol on its own. It'll send packets back, but it doesn't really have any mechanisms in place to ensure those packets get there and then do retransmissions or things of that nature. It really relies on a transport layer protocol, and more specifically, usually TCP to do that, which we'll talk about in a later module. But I do want to spend some time talking a little bit about IP addresses. I don't want to get into a ton of IP theory and how addressing works, because that's more of a fundamental networking thing, and that's not really what we're focused on here, but I will provide a quick crash course, just maybe a refresher for those of you who need it, and that way it frames the discussion of stimulus and response related to IP addresses a little bit better. So you're probably already familiar with what an IPv4 address looks like, but generally it's going to be a 32-bit or 4-byte address used to uniquely identify a host on an IP network. Ideally, it's a unique identification. Of course, we know that there's nothing stopping you from taking two devices and assigning them the same IP address. That's going to cause you a whole lot of problems if you try to communicate on either one of them. A lot of weird things are going to happen, and I've encountered far too many situations where I've had two hosts with the same IP address, and I've known about one of them, but not necessarily about the other. I've just had a host with just a ton of weird issues going on, intermittent communication I couldn't really explain, and then eventually either the operating system gave me a pop-up and told me there was a conflict, or I did some analysis and saw that there was a MAC address existing on the network that was also using the same IP address. So ideally, it's a unique assignment per network, but of course, that isn't really super enforceable on since this is an individual host type thing. So that makes it a little bit tricky. But in general, still, all IP packets contain a source and destination address. Now, they have those values. They can be anything. I can set it to maybe 0.0.0.0 depending on how I'm crafting my packet, and that's not going to be valid, but it'll have a value there. So you will see a source and destination in every IP packet, and generally those are going to be represented using what they call dotted quad notation, and this is what we're all familiar with. And you see on the screen here we have 192.168.0.1. That's the IP address we're all familiar with, and each area of that quad, each of those four sections represents a single byte or 8 bits, and you see that broken down on the screen. So to the far right in the lower order, the far right section of this, you see .1, and 1 represented in binary is 00000001. So it's a binary representation. You see that represented for all four sections here. The dotted quad, the decimal notation, is just a much easier way to display this. Obviously, it's a lot easier to remember that notation than the binary notation or even a hexadecimal one. So we use the dotted quad to express the IP addresses, which is what we'll continue to do almost exclusively throughout this course. Now, IPv4 has the concept of subnets, and what that means is that an IPv4 address is not just a solitary entity. It's really divided into two portions to provide two different functions. The first is the network portion of the address, which identifies the network the host belongs to. And then there's the host portion of the address, which identifies that host uniquely on the network. And this concept of subnetting exists so we can take an IP space and divide it into different sections and apply different routing and filtering rules and things like that, divide up our networks a little better. Nobody likes a flat network. You want good, nice segmented networks for security purposes and to properly direct the flow of traffic and not overwhelm certain subnets. So subnets are a really good thing. Now, the division of addresses is defined by what we call a subnet mask, and I have an example of that displayed on the screen here. You see at the right, we have an IP address 10.10.1.22, and it's divided into two sections. We have a network section and a host section, and we define that based upon a mask. And we've talked about masks a little bit already. We talked about masks when we were doing bit masking with filters, and a mask is basically where you just apply, you have binary data, and you basically apply another set of binary data to it, so to speak, and you mask the bits you care about, or the bits you want. So in this case, a subnet mask is a representation of those bits where we're masking the portion of the address that is the network portion. So if you'll see here, we have 10.10.1.22, and on the top we have the binary representation of that broken out into each quad. Below that, we have another binary set of data, and you see the first two quads are all ones, and that is the network portion. By masking those, by flipping those bits to a 1 or applying a 1 bit to those, we are saying this is the network portion of the address, and by leaving all the other bytes, the third and fourth quad, third or fourth bytes, zeros, we're saying that's the host portion. So every system will have an IP address and a subnet mask. And the subnet mask is basically telling the system how to read the address. And it's telling other devices on the network how to do the same. So it's saying in this case, the first 2 bytes of the dotted quad are the network portion. And the last 2 bytes of the dotted quad are the host portion. So ideally, on this network or this subnet, every other device is doing the same thing, and 10.10 is consistent across the entire subnet, but anything in the second 2 values, the .1 or the .22, can be variable as they define the unique host. And you can see here how you want to size these things appropriately, right? Basically, the fewer network bits you have, the more host bits you have, which means you can have a larger number of hosts with unique addresses on a particular subnet. So when you're doing network planning, that's one of the things you're doing is planning your subnet sizes, and you apply subnet mask with that in mind. On the flip side, you also apply subnet mask if you have a large number of individual subnets you want to have. So if you have a ton of different subnets you need to have, you're going to have a much larger network portion. Now, that said, a lot of people just use a standard, right? We've all seen 192.168.1. whatever addresses with 255.255.255.0 subnets. And that's just the standard a lot of people use for smaller networks. So not all networks are planned appropriately, and a lot of them use a wide variety of subnet mask and divisions between network and host portions of addresses. But all this to say, really what I want you to take out of this is that subnet mask exists to define what portion of the address is dedicated to the network and what portion is dedicated to the host. And I want you to keep that in mind as we go through, because that'll matter for some of the examples we're going to be going through. Now, with that said, one more thing that's worth mentioning here is that any packet with a destination address outside of a particular subnet are sent to a completely different address that's defined on an individual system. And this is generally going to be referred to as your gateway or your default gateway. And what we're basically saying here is, okay, I have a packet and it needs to go to a system that's not on my local subnet. I have no idea how to get it there, but my default gateway, or in this case, my upstream router, which is what that's usually going to be, it's going to know what to do, or it's going to have the best chance of anybody else on the network to know what to do. So any packet that's not on my subnet or destined for my subnet, I'm going to send to that default gateway address. And that's going to be important as we talk about the concept of external and internal addresses here in just a moment. So now I want to ask you a question. And that question is, can every device in the world have a unique IPv4 address? What do you think? Well, the answer is no. And the reason for that is simply that there's a limitation on the number of IPv4 addresses that exist. Of course, we have the dotted quad, so we have 4 bytes of available addresses, and that's not a lot. That actually figures out to a little over 4.2 billion possible addresses. And 30 years ago, that may have sounded like, yeah, we're never going to have that many addresses connected to the internet, but certainly now we do. We have corporations that have hundreds of thousands of devices connected to the network. I would venture to say the United States Department of Defense has more than this many devices connected to the internet on its own. So you see there's a limitation. We can't give every device its own unique IPv4 address. It just doesn't work. So how do we overcome that? If every device needs an IP address to communicate, but there's not enough of them, what do we do? Well, the answer there lies in something called network address translation, and it allows for this whole concept of internal and external IP addresses. And what that means essentially is that devices that are actually connected to the internet will have an unique assigned IP address that's accessible from other internet facing devices. But they kind of serve as this inherent border, right? And if you think of borders, you think often of firewalls and routers, and that makes sense because network address translation mostly happens on routers on externally facing devices. On most networks, you only have one device that's actually routing your communication to and from the internet. That external router serves at the border, and it's the only thing that needs an IP address that can communicate out on the internet. Everything else below that just needs to be able to communicate to that router via that default gateway address we've talked about, or to each other within the same network or within different networks on the non-internet facing network. So basically, we set up these choke points or these routers that are internet facing, and those each get a publicly assigned IP address. Now, different organizations can have multiple ones of those. If you have a central office and 3 branch offices, each branch office may have its own dedicated IP address. So you may have 4 of them at that point. But all the devices underneath or downstream of those particular routers are going to have internal addresses that are not necessarily routable on the public internet. So that allows us to duplicate things. That's why you see addresses like 192.168.0.1, but those exist in every network. They exist in my network, your network, everyone else's network. They don't have to be unique because they're not publicly facing on the internet. That's what externally assigned unique dedicated addresses are for. So, and you have to remember too that routers also have multiple interfaces, and that's the key point here. Routers route traffic from one network to another, and often that means routing traffic from your local network to the internet, to things upstream out on the internet. And there's an example of this depicted on the screen. This kind of represents a router, right? As you have 2 interfaces on it, so 2 physical cables probably plugged in. All of the things on your network, all the workstations, all your laptops, your printers, etc., have addresses in this 192.168 range. And that's not a routable internet address, but allows them to communicate with each other, and they all have a default gateway programmed in, which is 192.168.0.1. That's how they know anything that's not on my subnet, I want to send it to that address, and that's going to be my router, and it's going to know what to do next. So the router now has an upstream interface where it's connected to the internet. Here it has the address 42.52.14.10. This is a unique address. Only it has it, and it's assigned by the Internet Assigned Numbers Authority, or IANA. It has that address, and it can use that to communicate through its ISP to anything else out on the internet. And it can communicate out to other routers that have public-facing addresses that can then use network address translation to translate communication into internal addresses rewritten for its downstream devices. So hopefully that's not too confusing for you. I don't want to get too in-depth on NAT here, but I do want to give a brief refresher on it, maybe if you weren't familiar how that worked, because it is going to manifest a little bit as we talk about normal and abnormal stimulus and response for the IP protocol.